In this video, we solve problem 12.5.053 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to consider the following function, y equals natural log of x. And then we're asked to find the point on the curve at which the curvature k, or kappa, is a maximum. And we're looking for a location x, y on that curve. And then we're asked in part B to find the limit of the curvature k as x goes to infinity. Now, we had 5 different formulas for curvature, but if we have y as a function of x, we said we should use this formula for curvature. Now, this will give us curvature as a function of x, and then in part A, we're asked to maximize that curvature. We will maximize the curvature using techniques from Calculus 1. So we can either use the first derivative test or the second derivative test, depending on what looks sort of easiest to us, most computationally straightforward after we've evaluated this expression here. So that's the plan. First, we'll find the curvature. And we'll just use this formula, which is easy enough to use. To use the formula, I need to compute y double prime. So first I'll write y equals natural log of x. That means y prime is 1 over x. Since I'm taking the derivative again, I'll write that as x to the negative 1. Y double prime requires us to use the power rule. So we'll bring the power down, multiply by x to the 1 less power. The absolute value of this function goes in our numerator. And then in the denominator, we've got 1 plus y prime squared raised to the 3/2. So k of x, or our curvature as a function of x, is this y double prime divided by 1 plus y prime squared to the 3/2. And y double prime is negative 1 over x squared. If I write that with a positive exponent 2 in the denominator. And y prime is 1 over x. Of course, the absolute value of negative 1 over x squared is positive 1 over x squared. X squared is always positive, except for when it's 0. And then this would be undefined. And of course, the absolute value of negative 1 is 1. And then, of course, when we simplify this fraction here, we'll square the numerator and denominator. So we'll have 1 over x squared there to the 3/2 power. Now, under this, or inside this set of parentheses, where I've got this expression to the 3/2, I might want to get a common denominator. So I'll write that as x squared over x squared. And now that I have a common denominator, I can add the numerators and keep the common denominator. And remember, all of this is raised to the 3/2 power. So if I've got a fraction raised to the 3/2 power, I can raise the numerator to the 3/2 power and raise the denominator to the 3/2 power. This numerator doesn't simplify because we're adding those expressions, so we'll leave it alone. Now this would typically simplify, but remember, this tells us to cube something and then take the square root. Typically, I would just multiply the exponents and I'd get x cubed, but that's not exactly right because I'm taking a square root. I'm not going to get x cubed. I'm going to get x cubed when x is positive, and I'll get the absolute value of x cubed when x is negative, because that's really a square root. A positive square root will always yield something non-negative. So this will be an absolute value of x cubed, not x cubed. And I hope that that makes sense why. Let's write that down. I'm taking x squared and I'm writing to the 3/2 power. That's the square root of x squared cubed. And that square root will always give us a positive number. So the square root of x squared would just be the absolute value of x, and then we're cubing that, which we could say is the absolute value of x cubed. So either way, whether you put that 3 on the outside of the absolute value bars or the inside, we're going to get this over here. That was scratch work for a different problem. Okay, so I've got a fraction divided by a fraction. So we will multiply by the reciprocal. And again, I can put that 3 inside or outside of those absolute value bars. And we have this right here. And this will reduce with 2 of those x's. And so we'll just end up with the absolute value of x over x squared plus 1 to the 3/2. Ooh, now when we differentiate, it's kind of tricky because of those absolute value bars. So maybe we actually want to change it back to a square root expression. Let's square that and take the square root. And then we'll have the square root of x squared in the numerator. And this denominator we can think of as the square root of x squared plus 1 quantity cubed. And I'll write it like this. X squared, I'll write it as a larger square root. The square root of a divided by the square root of b is the square root of a over b. If you're saying, why would you do that? It just makes differentiation easier. Okay, so that's k of x. And I want to take the derivative of k of x because I want to find the maximum of that function. Now remember from calculus 1, how we find the maximum value of a function. You've got a couple of options. In calc 1, we talked about the first derivative test and the second derivative test. We use those to optimize functions. Remember what optimize means. Optimize means to find the optimal value of a function or to find the minimum or maximum value of the function. First thing we do is we find out where the derivative is 0 or where the derivative is undefined. We call those critical points. So to find critical points, we compute the derivative of the function of interest. In our case, it's the curvature function. We compute k prime. We set k prime equal to 0 and solve for x. And then consider x values where k prime is undefined. X values where k prime is 0 are potential minimum and maximum values of k, and x values where k prime is undefined are potential minimum and maximum values of k. So let's say our curvature function looked something like this. Well, I could have a minimum or a maximum anytime the derivative is 0, and the derivative is 0 at the top here and at the bottom here and at the bottom or at the top there. And then the derivative is undefined at that cusp. So what we're trying to find when we find the critical values are these x values. That x value, I'll call it x1. That one is x2. That one, I'll call it x3. And that one, I'll call x4. So we're trying to find those values that are potential mins or maxes by setting the derivative equal to 0 and finding out where the derivative is undefined. And then we'll have to decide whether each of those values corresponds to a minimum or a maximum. And we can do that using the first derivative test or the second derivative test, but we'll do that when we get there. Of course, this is a cartoon. This is not actually a picture of k of x. We don't know what the curvature function looks like, and we could use a scientific or a graphing calculator to find out, or we could use desmos.com to find out if we were really interested. But let's use calculus. Let's use a little bit of symbolic manipulation to figure out what that graph looks like. So we have our curvature function is x squared over x squared plus 1 cubed, all raised to the 1/2 power. And I want to know where k prime is either 0 or undefined. So the first thing we will do is compute k prime. And because we've got a function raised to the 1/2 power, we'll use the chain rule. This is our inside function. Remember, the derivative of a composite function f of g of x is the derivative of the outside evaluated at the inside times the derivative of the inside. And so what we're doing here is first we're taking the derivative of a function to the 1/2. The derivative of something to the 1/2 is 1/2 of that function to the negative 1/2. You put the inside function back inside, and then you multiply by the derivative of the inside by the chain rule. Okay, I'm gonna keep going. Now, if I have a fraction raised to a negative power, I can simplify that. I might want to write it with a positive exponent. So we'll just flip that fraction and make the exponent positive. So I can write this as x squared plus 1 quantity cubed over x squared raised to the positive 1/2 power. Okay. And this derivative requires the quotient rule. So we'll have the bottom function times the derivative of the top function with respect to x. That's low d high minus high, which is x squared, d low. Now I've got a function nested inside another function, so we have to use the chain rule again. The derivative of a function cubed is 3 times that function squared. And then we multiply by the derivative of the inside by the chain rule, which is 2x. So this is low d high minus high d low over low low. So of x squared plus 1 quantity cubed, that's the bottom function, squared. All right, so that's our k prime. We want to know when it's equal to 0. It'll be easier to figure out when it is equal to 0 if we do a little bit of algebra. Let's simplify this. So I have 1/2 times this quotient raised to the 1/2. And then over here, I've got x squared plus 1 quantity cubed times 2x minus 3 times 2 is 6. 6x times an x squared is 6x cubed times x squared plus 1 quantity squared. And I've got a power raised to a power. We multiply the exponents. So that's x squared plus 1 to the 6th. Now, when I look at this expression and this expression, I see that they both have an x squared plus 1 in common. So I'll factor out an x squared plus 1 from those. Actually, they've got an x squared plus 1 cubed and an x squared plus 1 squared. So they've got an x squared plus 1 quantity squared in common. And then I say to myself, okay, x squared plus 1 times what will give me this? Well, I'm missing a 2x and I'm missing another x squared plus 1. So I write that down. And then I say x squared plus 1 quantity squared times what will give me this? Well, I already have that taken care of. The only thing that's missing is that negative 6x cubed. We have that right there. So keep going. You've got 2 of these and 6 of those down there. So you'll have 4 of those after you simplify. In the numerator, if you distribute that 2x, you'll have 2x cubed plus 2x minus 6x cubed all over x squared plus 1 quantity squared, or quantity to the 4th, sorry. And this 2x cubed minus 6x cubed is negative 4x cubed. So we have 2x minus 4x cubed all over x squared plus 1 raised to the 4th. Now I see that this has a factor of 2x and there's a 1/2 over there, so I will keep simplifying. Factoring out the 2x, I have 2x times 1 would give me that first term, and 2x times negative 2x squared would give me my second, all over x squared plus 1 raised to the 4th. That 2 and that 2 will reduce. So we end up with this. Wow, that's a lot. That's okay. Now you may be tempted to simplify further. I know I am. I know I see that square root, see that 1/2 power, which is a square root. I'm thinking square root of x squared is usually x. It's actually absolute value of x. And that absolute value of x will cancel with this x. Most of the time, you're going to get either 1 or negative 1, depending on whether x is positive or negative. So we could do that. And then we also have this x squared plus 1 quantity cubed here, raised to the 3/2, and an x squared plus 1 raised to the 4th over here. And those could simplify a lot. But we have to remember that the signs, we need the square root to always give us a positive number. So I guess we could simplify a little bit further, but we have to be really careful. So let's keep going. This is x squared plus 1 to the 3/2 if I apply that 1/2 power to this and this. And then down here, I'm thinking of this as the square root of x squared, which is the absolute value of x. Okay. And so we've got x divided by the absolute value of x. I'll factor that out. Then this x squared plus 1 to the 3/2 and the x squared plus 1 to the 4th will simplify. 3/2 minus 4 would be 3/2 minus 8/2. That's negative 5/2. I end up with an x squared plus 1 to the 5/2 in the denominator. And I still have that in the numerator. Check it out, make sure it still works. This times this is up there. This over this simplified to that, and that's there. Okay. Now, k prime will equal this whenever x is positive, because if x is positive, this is just a 1. Now, when x is negative, this is a negative 2 divided by the absolute value of negative 2. Well, that's just going to give me a negative 1 every time, right? Because if x is negative, it's going to be a negative divided by the same number but positive. So I'll always get negative 1. So in that case, I'll have a negative 1 times the quantity 2x squared, or 1 minus 2x squared over this. And of course, k prime is undefined when x is 0. Okay, so now we want to optimize this Calc 1 style. That means we need to figure out where k prime is undefined. We know x equals 0 is one issue. And we also need to find out where k prime is equal to 0. So let's say that k prime is undefined at x equals 0. So that is one critical value, provided that x equals 0 is in the domain of the original function. And it is. This is well defined at x equals 0. We just end up with 0 over 1, which is 1. Oh, actually, We do get 0 over 1, which is 1 from that simplified version, but remember what K prime or how K prime was defined over here. So from this, we see that this is not well defined for x equals 0. Oh, actually, we can make a couple of other restrictions, which will help us as well. Y is equal to natural log of x. So the domain of this is 0 to infinity. So we're only interested in positive values of x. Well, that changes things. We're doing a lot of little symbolic manipulation just in case x was negative, and it turns out to never be negative, not in the domain of this function. So with that in mind, let's go back to all of this. We don't have to worry about K prime being undefined at x equals 0 because x equals 0 is not in the domain. X is never negative on the domain. So this is our K prime. The domain of natural log of x is 0 to infinity. So we're actually simplifying this function here. That's nice. It's going to make it much easier. So here K prime is never undefined because x squared plus 1 is always greater than or equal to 1. This x squared is always greater than or equal to 0. I add 1 to it, it's always greater than or equal to 1. So we're never dividing by 0. And x squared plus 1 is always positive. So we're never taking even roots of negative numbers. So we're good. This is always well defined. The only time that this will be 0 now, that's our concern, is when this fraction is 0. And the fraction is 0 when the numerator is 0. So we'll take this inequality, or excuse me, this equation and solve for x. So add the 2x squared to both sides, divide by 2, solve for x, you'll get plus or minus the square root of 1/2. We're only interested in the domain, which is 0 to infinity. So 1 over the square root of 2 is our single critical value. Because that value is not in the domain of natural log of x. Okay, now we were asked to find the point on the curve at which the curvature is a maximum. Now we only have one critical value. The question is, does that critical value correspond to a minimum or a maximum? Are we at a point like this or at a point like this? Or maybe it's at like a flat point where we've got a derivative of 0 and the function just keeps increasing, or maybe we've got a derivative of 0. Well, it was going to be increasing over here as well. Maybe it's a derivative of 0 and then it's decreasing. We want to know is, does this x equals 1 over square root of 2 correspond to a minimum or a maximum, or neither? To find out, we can use the first derivative test or the second derivative test. Okay, now remember what the first derivative test says. The first derivative test says that if you're at a critical point and the graph looks like this, so let's say we're given, or we've already found that C is a critical point, given C a critical point. If the graph looks like this, so that the derivative of the function goes from negative on this side to positive on this side, but then f prime of C is equal to 0. Well, since it's going from decreasing to having a 0 slope and then to increasing, then the function has a relative minimum at x equals C. So we'll say if f prime changes from negative to positive, f of C is a relative minimum of the function f. Now, if alternatively, locally, if f prime of c is 0, but f prime of is positive on this side, so that the function's increasing, and f prime is negative on that side, so the function's decreasing, the function's going up, and then it has a 0 slope, and then it's going down. If f prime changes from positive to negative, so that it goes from increasing to having a 0 slope to decreasing, then f of c is a relative maximum of f. Now, I drew these pictures where f prime of c was equal to 0, but I could have just as easily drawn them where f prime of c is undefined. So you might have a graph like this, or a graph like that, but it'd be increasing, undefined, decreasing, just like we have increasing, 0, decreasing. Either way, if it's going from increasing to decreasing, or increasing to decreasing, whether it looks like that or looks like that, we're going to have a relative max. And the same is true here, whether the graph looks like that and it's nice and smooth at the bottom, or if it looks like that and it has a cusp at the bottom, we've got a relative min. Now, if f prime does not change signs at c, so the function maybe goes from increasing to having a 0 slope to increasing again, or decreasing to having a 0 slope to decreasing again. So f prime is positive, then f prime is positive, or f prime is negative, then it's 0, then f prime is negative. Then that point where the slope is 0 is not a minimum or a maximum. So if f prime does not change signs, at x equals c, f has neither a min nor a maximum. Okay, so that is this is called the first derivative test, because we're looking at how the first derivative changes. And the second derivative test, does not deal with these cusps. It only deals with these two cases. Yeah, really these two cases. If f prime of c is 0 and the graph looks like this, the graph is concave up. So we say if f double prime, or f prime of c is 0 and f double prime of c is positive, that means the graph is going to look like this and we'll be at the bottom. So we'll be at that point at f of c will be a relative minimum, or the function value f of c will be a relative minimum. And that's just because if the second derivative is positive, we know that the graph is concave up. Now, if our derivative is 0, so we're either at the bottom or the top of something, and f double prime is negative, that means our graph is concave down. So if it's concave down and we're at a 0 slope, well then that function value must be a relative max. So you just sort of decide from here whether you want to use the first derivative test or the second derivative test. Either one is fine. Either one will allow us to determine whether our function has a minimum or a maximum. You just choose. Now, let's look back at our work for k of x. Our curvature function was this. And we're only interested in this on the domain of the function y. Y was natural log of x. So our domain is 0 to infinity. And k prime turned out to be this, also on 0 to infinity. Oops, there should be a 2 there. And the question is our single critical value x equals 1 over the square root of 2 a minimum or a maximum of this? If you want to find out whether that x value corresponds to a minimum or a maximum, we can either look at this first derivative and see where it changes signs, or we can compute the second derivative of this. It's up to you. I think most students would probably rather use the first derivative test in this case, because we can simplify this expression a little bit. Now, I know it's a little bit counterintuitive, but I think this will make it a little bit easier for us. I want to think of this as a difference of squares. I want to think of this as a squared minus b squared. We know from algebra that a squared minus b squared factors to a plus b times a minus b. So if a squared is 1, a is 1. And that means I can factor this to 1 plus something times 1 minus something. Now, if that was just 1 minus x squared, we'd have 1 plus x and 1 minus x. Since we've got 1 minus 2x squared, I need a square root of 2 here. So I'll have square root of 2 times x there and square root of 2 times x there. This times this would give me a 2, and the x times x together will give me that x squared. So it still works out. You don't have to factor it this way to figure out where k prime, or whether k prime is changing signs at x equals 1 over the square root of 2, but I think it makes it simpler because now I'm thinking of k prime as a product of this and this, and it's also a product of those two and 1 over this expression here. So the sign of k prime is entirely determined by the signs of this factor, and this factor. Okay, so let's now use this factored version of k prime to make a sign chart for k prime. And we're only interested on the in the interval from 0 to infinity, and our x value of interest is 1 over square root of 2. And I've got 3 factors, 1 plus 2 square roots of 2, or 1 plus square root of 2 times x, excuse me, 1 minus square root of 2 times x, and then the factor x squared plus 1 to the 5 halves. Now, it does not matter about what x is. If I square it and I add 1 to it, I'm going to get a number that's greater than or equal to 1. So I'll take that number and I'll raise it to the 5 halves. That'll definitely be positive. Now, if x is positive, then I multiply it by the square root of 2 and I add 1, it'll still be positive. So the sign of k prime is entirely determined by the sign of this factor. So the question is, if x is greater than 1 over the square root of 2, now is this positive or negative? Well, square root of 2, I believe is about 1.4, if I'm remembering correctly. Yeah, it's about 1.4. So this is 1 divided by 1.4. It's a little bit less than 1. So if I substitute an x equals 1, that's an x value on this interval, I can determine the sign of this factor on this interval from 1 over square root of 2 to infinity. So I'll have 1 minus square root of 2, which is a negative number. And then over here, I want to choose something that is between 0 and 1 over square root of 2. 1 over square root of 2 is about 0.7. So let's just plug in x equals 1/2. So I have 1 minus square roots of 2 times 1/2. And I get about 0.29, which is positive. So k prime is this positive times this positive divided by this positive number. Positive times a positive divided by a positive is positive on this interval, and it's a positive times a negative divided by a positive, which is negative. So that means the function goes from increasing over here to having a 0 slope at x equals 1 over square root of 2 to being decreasing on that side. So we're going to have a relative max at 1 over square root of 2. Now let's go back to the problem statement, the question that we were asked at the very beginning. we want the point on the curve at which the curvature is a maximum. So we know that the curvature is a maximum at x equals 1 over square root of 2. I want to know what location that is on the curve given by y equals natural log of x. So I just replace x with 1 over square root of 2. That's one way we could write it. You can just enter that, that's fine. Or you can use log properties. Log of a over b is log of a minus log of b. Log of 1 is 0, so you could write that. Square root of 2 is 2 to the 1/2, and you can bring that power down out front. So we'll have 1 over square root of 2 as our x value, and negative 1/2 natural log of 2 as our y value. Now, as far as I'm concerned, this is fine. This is a fine answer for the point where our curvature is at a maximum, the point on the curve where the curvature is at a maximum. But if we're checking our answer in the back of the book, or we're wanting to simplify as much as possible, we could use these log properties that I just mentioned. So let's see, I use the fact that log of a over b is log of a minus log of b. I use the fact that log of a to the n is equal to n times log of a to write that square root as a 1/2 power and bring that 1/2 out front. And I use the fact that natural log of 1 is 0, and that's true because e to the 0 power is 1. Okay, so that is the answer for part A. Little bit of a Calc 1 review, which is always good. And now we want to know the limit of the curvature function as x goes to infinity. This is also a Calc 1 review. So I'll just use this right here. So curvature depends on x. And the maximum curvature of that logarithmic function, y equals natural log of x, which we all know kind of looks like this. It occurs at x equals 1 over square root of 2, which, let's see, what was that? About 0.7. We're going to have a maximum curvature there, and then it sort of flattens out, and then it's sort of flatter over here as we get close to the y-axis. So the curvature changes as x changes. And the question is, as x goes to infinity, what's happening to that curvature over here? Now we know that if y equals natural log of x, the slope of that is 1 over x. So that slope is getting very close to 0 as x gets large. So when x is 100, the slope of the curve is 1 over 100. It has a tiny, tiny positive slope, but the slope is 0.01, like it's small. So with that in mind, you might say if the slope is that small, what would its curvature be? Now remember, the curvature is related to the second derivative. If the first derivative is really small, and the second derivative is that function, it's even smaller as x goes to infinity. I expect this to go to 0 actually, but let's write down our curvature function. It was x squared over the quantity x squared plus 1 cubed, all raised to the 1/2 power. Now this function, this square root function, is continuous, so you can bring the limit inside. So you can just think of this as the square root of the limit as x goes to infinity of this expression. Well, as x goes to infinity, I think that we can all see that this is going to go to 0. We've got a polynomial of degree 2 in the numerator and a polynomial of degree 6 in the denominator. And obviously the polynomial of degree 6 is going to get larger faster than the polynomial of degree 2. But technically it's infinity over infinity indeterminate form. You might say to yourself, well, how can I get rid of that problem? How can I get rid of the infinity over infinity indeterminate form problem? Well, one way that we can do that is we can divide the numerator and denominator by the same thing. We've got to be careful here because of this x squared plus 1 being in parentheses. I'd really like to divide everything by x to the 6th. So I'll divide the numerator by x to the 6th, and I want to divide the denominator by x to the 6th. But I can't think of it as an x to the 6th over here. I want to think of it as something cubed. So I'll divide the numerator by x to the 6th, and I'll divide the denominator by x squared cubed. And if you're saying, why on earth would you do that? It's just because I want this cubed divided by that cubed to be something that I can rewrite as a fraction cubed. Now, if you just said the answer is 0, that's probably fine. X squared over x to the 6th is going to give me a 1 over x to the 4th. But if we're trying to get rid of that infinity over infinity indeterminate form, I like to show my work. I've got this expression cubed over this expression cubed. So now I can write that as a fraction cubed. And now I have a monomial in this denominator, so I can just divide each of those pieces by x squared. X squared divided by x squared is 1, and then I've got a 1 over x squared there, and we're cubing it. As x goes to infinity, this goes to 0, and this goes to 0. So I end up with 0 over 1 plus something going to 0 cubed. This expression under the radical goes to 0, square root of 0 is 0, so the limit is 0. So that means as x goes to infinity, the curvature approaches 0, which is exactly what we see when we look at the natural log graph. That graph is flattening out. The slope is always tiny and positive, but it gets smaller and smaller and smaller and smaller. And so as x goes to infinity, that line is not horizontal, but it's getting very, very, very close to being horizontal. And that curvature, as a result, is approaching 0. Okay, so that is how we solve problem 12.5.053. Please let me know if you have any questions about that problem. It's just a little bit of a Calc 1 review.